let's take a look at how we might use a couple of debuggers to help us fix problems and potentially problems during the exam. Of course, if you're very careful about how you write the program, think about it a little bit, type in the code carefully, test it incrementally, which is what I did for my for the MIPS example, and I had no errors at all. So the code ran first time. Similarly for the C program, test it incrementally as you write it, and you may not have bugs, but if you do, first thing you've got to do, find them. And find them is the most painful part of debugging. Right? So you run your program, it says segmentation fault, or the MIPS goes into an infinite loop, spewing out invalid instruction at address, invalid instruction at address, things like that. So trying to work out what caused that is potentially the trickiest thing. Once you've found what caused it, it's usually obvious what the problem is, and you can fix it. All right, so we have tools that will help us with this. Pretty much all debuggers allow you to do two things. Control the execution of your program, so you can stop it at a certain point. You can step it, run it step by step by step. And the other thing you can do is you can look at the state of the program. Now, something like QtSPIM sort of pushes the state at you all the time. Something like GDB, you've got to go looking for the state information. So you actually have to ask it, print a value of some variable or other. All right, so QtSPIM is a debugger for SPIM. Obviously, the first thing you've got to do once you start QtSPIM, you've got to load your program. Once you've done that, it'll show you all the registers down the left-hand side, show you the code in the main window. There's a couple of tabs at the top of the window. I probably should ping it up, actually, so I can talk about this stuff. Might see it. It doesn't really fit nicely on the screen when it's this big, but that's why. Let's see if I can. No, that'll have to do. Right, so we've got the registers down the side. By default, it shows the integer set of registers. You can make it show the floating point registers. And over here, you can look at the memory, either at the code part of the memory or at the data part of the memory using these tags. So that'll tell you what's in the .data bit, and this will tell you what's in the .text bit. Now at the moment, importantly, we can see that we have no main program. So the address is, and I can't make it bigger, hopefully that's big enough, and if it's not, move forward. If it says the address of something is 0, it means it doesn't know that symbol. So at the moment, there's no main program loaded in. What else? When you execute an instruction, if you're doing it step by step, the thing that just changed goes red, which is very handy. So you can see what the program just did. Anyway, so that's kind of what it looks like. So you can see the registers, the code and the data. Can't see them all simultaneously, but you can flip between the code and the data if you think there might be something that you've done wrong in the data segment. You can run programs, so you're just using that little symbol up there, and all of these icons, all of these icons, if you hover over them, they tell you what they do, which is handy. So you can run the program, you can set breakpoints, which requires something not nicely documented, but a right mouse click on an instruction will let you set a breakpoint, which basically means you can run the program. When it reaches that instruction, it stops, and then you can start looking at the state, step-by-step execution and so on. So you can do, you can step one instruction at a time. All right, so let's just do a demo. So I wrote a trivial little MIPS program. It's got a function call, and it's probably easier than what you get in the prac exam, but it's just basically the same kind of thing. What we'll normally do in the prac exam, we'll give you a working main program. We'll give you a function that you have to write. We'll call that function, and we'll print the results from that function. So this one simply runs through and finds the largest number in an array of positive integers. All right, so what do we see here? So max is the function name, takes two parameters. One is the address of the array, and the other one is the number of elements in the array. And then it just iterates through the array and checks whether the next element is bigger than the biggest one it's seen so far. Initialises big to -1 because we're talking about positive ints. So we guaranteed that the first element in the array is going to be larger than big. Okay, so I've written a MIPS version of that, which isn't that. And this MIPS version I can run, I can run by typing, this is the working version, okay? And it just does that. So it runs, prints out the result, which is correct because the array that I actually used in the program has 8 as the largest value. Let me see, I think the version that we're going to debug has an error. So when I run it, it does that. And I'm sure you've seen that before. Okay, that's just going to go on and on and on. Interesting. It's telling you that there's a problem at that particular address. We'll see what that address corresponds to in a minute, but it keeps retrying to do things at that address, so it's not really getting very far. So let's, I suppose we should have a look at the MIPS code before we load it up. So it's pretty standard. We got these names. We've got some data definitions. This is the array I was actually using. Might have been different to the one that was on the other slide. Obviously there are 10 elements in the array. The main program sets up a stack frame. Hopefully all remember how to do that. Uses one of the S registers, so it has to save that. And then loads up the arguments, calls the max function, grabs the result that comes back in $v0, saves that, and then prints out the message, prints out the saved return value, and then prints out a new line, and then cleans up the stack. Okay, nothing special about that. And the max function is pretty much as you'd expect as well. Set up the stack frame. In this case, we've got 2 local variables, and we'll stick the 2 parameters into S registers as well. So we've got more things on the stack. We grab a copy of the 2 parameters, the 2 parameter values, and then we initialize the iteration variable and the big variable, and then we've got our for loop, which runs through, computes the address. We're multiplying by 4 because the values in the array are int values. We compute this address, and then we dereference the address to get the next value. Check whether it's larger than the biggest one we've seen, and if it is, we'll make it the largest one. Otherwise, and even if we do that, we add 1 to the I variable and then go back to the top of the loop. Having finished, we make a copy of the big variable as the return value and then clean up the stack frame. Okay, so looks all right. Doesn't work though, so let's try and find out why. All right, here's QtSPIM. So I can load it up using this. La la la. Before I left my office, this was set up so it would nicely find that value. Okay, so now it's loaded up. One way you can tell that you've actually loaded something is now the value of main actually has a number. So it knows that the main label is at 400024. Right, so we could just run it. And it's going to tell us that this exception occurred. So the same thing. And it tells us, well, hard to see this, that it's happened at address D8, which, if we look down, thank you, went too quick there, but it was that address there. Not sure why that would be wrong. Let's take a look at the values of some of the registers at this point. So $8 is register 8, corresponds to this was the address that we computed for the current element of the array, and we look at the value of that register, 0. That sure as hell doesn't look like a valid address for and part of that array. So something has screwed up $A8. So we're going to need to work our way back through and find out what actually happened. So probably the simplest thing to do once you've messed it up like that is just to reload and reinitialize. So that set everything back to square one. And you can do that using that second button there. All right. Now the problem that we came across was in the max function. So let's set a breakpoint for max. Now where does the max function actually start? And we can see there's a jump and link to max, and we can see that the address of max is 4000 AC. So if we go down here, that is going to be the first instruction in the max function. Okay. So let's set a breakpoint there. So right click, set breakpoint, and you get a little hand there saying stop when you get to this point. And then you can run the program again. So the execution stopped at the breakpoint. Now what we want to do is watch closely what happens when this runs. So let's do a single step. So here we're setting up the stack frame. I guess we probably want to be careful to make sure that we're doing that properly. So if you start looking at the values in SP, which happens to be off the screen down here, that looks like a valid kind of value on the stack. Anything with 7FFF is a stack address. Then we've loaded up other stuff on the stack, and now we're starting to save stuff. Storing the current value of S0. The current value of S0 is 0, so that's not super interesting. We store that on the stack, store that on the stack. Store the value of S2, store the value of S3. Right, so now we've almost set up the stack frame once we do that add. Right, now we've set up the stack frame, now we can actually start executing the code for the body of the function. All right, first thing it does, it moves the value of A0, which is the address of the array, into $S0. So let's just step that instruction, and we can see that the value, the register S0 changes, and it's got that value there. Now I guess if we really wanted to, we could go and check the data and see what's the location it's talking about. It's talking about 10010040. 30. Yeah, so, oh, interesting. Why is it saying they're all zeros? Oh, is that the right address? Yes, it is. I would have expected to see, oh, sorry, if we look around here, 3568221. All right, so that's where the array is. So it's interesting that, that address is actually correct. It's not, it's 04, not 40. All right, so it's loaded up the address of this. So that's 4 zeros, and that's the new line character, and then 3 zeros and a 4 is this, and that's the start of the array. So the number 3, then the number 5. And if you went back and looked at the program, hopefully we'll see, so 3, 5, 6, 8, 2, blah, blah, blah. So at least we know we're looking at the right thing and we've loaded up the right address. All right, next thing to do another single step. So the next instruction is going to load the count of the number of items which should have been put into register A1. Wahoo! That sure as hell does not look like a count of the number of items. So there are only 10 items in the array. That's definitely not the number 10. So in fact, that to me looks like an address. Interesting. So somehow into the second parameter we've got an address rather than the value 10. Now at this point you might think, maybe I used the wrong load instruction, and you might go back and have a look at your program and see where did I set up the value for the parameter. So it's in the main program, it's down here, so looks like this one worked all right. So it loaded up the address of the items array. Here we've loaded the address of the nItems object. I don't think so. What's wrong? I didn't want to load the address of nItems, I actually wanted to load the value of nItem. Okay? So the problem there is we basically just used the wrong load instruction. So if we actually went and changed it, then the program would start working. So that was a bit too easy, that debugging. Even though it looked like a mess initially, we can see that the wrong value got put into register A1 before we called the max function, and if we weren't convinced of that, we could potentially go back and check and single step through the main program just to see what was actually going on, and we'd see that once we got to this instruction that we would have loaded that large address value. And I just realised that I actually said the wrong thing before. This is actually the count. It's not the new line character, it's actually the value of 10, which is the count of the number of elements in the array. And if we'd gone and looked at the program, we would have seen that nItems is first, and then the items array follows after nItem. So that was the problem there, and we could work this out. Basically, once we got to this point in the program, and we look at, all right, we're trying to load the value of the second parameter, or up here, we've loaded the value of the second parameter into the register S1. S1 has a ridiculous value. We knew what we expected. The value of that second parameter should have been the number of elements in the array, which is 10. Okay, so if you know that's what's supposed to happen, then you can see that it obviously hasn't happened here. So working backwards from that, you'd say, all right, the wrong value was in A1. How did that value get into A1? Well, one thing you could check is you could look here and make sure that none of this code had messed up the value of A1, which is possible. And if we wanted to do that, I better break the program again. put it back to that. So what we could do, we could just go back, reload it again, max.s, this is the buggy version, I hope, blah, blah, blah. And we could work out where is it setting up for the call to max. That's there. So potentially we could put a breakpoint a little bit before that. So let's stick a breakpoint here, run the program again, it'll hit the breakpoint there, and then we can start single stepping. So we're about to load the address of items into register 1. So that's correct. If we go back, oh, it's not quite correct. If we go back and look at the code, but as soon as we do this OR, that's the correct address for the items array. So happy with that. Execute the next instruction. One thing to keep in mind, this shows you the instruction that it's about to execute. So we just executed the previous instruction, so we execute this one, then we see that A1 has ended up with this value there. And that was the value that we saw once we got into the max function. So that's the point where things went wrong. And then we've got to work out why, and we'd say, wait a minute, why am I loading the address of n items? I actually want the value of n items. I want the value 10, not the location of that n items object. So if I were to fix that, write it out, and then probably the easiest thing to do, and if you're in the middle of an exam, you're obviously going to run that check script to make sure, but you can easily check it yourself. And now it works. Let's break it in some other way. Now this is where you should all close your eyes while I make a change that breaks the code. Otherwise, if you see what I'm doing, it becomes a little bit boring. Let's see. I know what we can do. We can mess up the loop and we can forget to increment our loop variable. All right, so easiest thing to do, just comment that out. Okay, what happens? So first thing we've got to do, we've got to look at the symptoms. La 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 la. So we're not incrementing the loop counter, it's just going to go round and round that loop forever. Okay, so there's no point in sitting around watching that do nothing. Let's see how we can diagnose that. So load the buggy program up again, and we could just try running it. And it seems to stop at a certain point. Now, I'm not sure why it stops here. Possibly there's some kind of timeout happening. But if we really, if we didn't have a clue and we didn't want to start running knowing it was going to be an infinite loop, we could stick breakpoints, at the start of the max function, say, maybe, it could be a loop, could be an infinite loop in the main program. But of course, you go and look at the main program, there are no loops in the main program. So it's clearly not going to be that. The only loop is in the max function. So if we were to just single step this a little bit, la 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 la, and pretty soon it would become clear that we're just going round and round this for loop in the max function. All right? So now we need to start looking at the variables that control that loop. And this branch on equal, this is the point where we check whether we've reached the end of the loop. So we need to look at the values of the registers as we're about to execute this function. So $1, all right, $1 isn't super interesting because it's an internal register that just contains status values that we get from Oh, sorry, I'm looking at the wrong bit. That's not that test. Where is it? Oh, no, it is that test. All right. Branch on greater than or equal to the end of the loop. All right. So the actual test, and I think Jashank, when he wrote the code for the first assignment, he actually used SLT in a few places, which kind of, so when you write a branch on greater than or equal in MIPS, in your MIPS code, it actually gets turned into two instructions here. So there's a test instruction and then a branch. So the thing we need to look at is what happens at the test instruction. So we're comparing register 18, which is that one there, and we're comparing it against register 17, which is that one there. It's got an A. Hopefully we know from our knowledge of hexadecimal that that's the value 10. So we're comparing the value in register S2, and if we go back to our code, we know that S2 corresponds to the variable I, and okay, it contains the value 0. And we're comparing that to 10, obviously it's going to be less, so we're not going to exit the loop. So if we just start single stepping again, when we go back to the top of the loop and make this test, we'd pretty soon notice that S2 is 0. And it doesn't matter how many times we go around the loop, S2 is always equal to 0. Okay, it never gets changed. So we could pretty soon, hopefully from seeing that, figure out, maybe S2 needs to be updated. And we'd look through our loop and we'd say, hey, I've forgotten to update the loop variable. Well, hopefully we would. But at least you got a lot of clues from the fact that the value of that register never changes. So really, what you're looking... Oh, why have we got that? Interesting. What you're looking for is clues as to why your code isn't working properly. All right, so that's an easy thing to do if you're getting to increment your loop counter. Yes, here's another thing that we can try. Forget to set up the return value. I'm not sure exactly what's going to happen here. I didn't try that. So let's write that out and run it. And it tells us that the maximum value is 4, which it's clearly not. We know that it's 8. So how come? So once again, we go back in, and this time it would make a lot of sense to, let's reload the thing. So a couple of things, a couple of places we could check is after we called the max function, maybe we're overriding the return value. So we could look up here, where's the call to max, jump and link to max. When we come back from here, it doesn't look like we're messing things up, and in fact, we're actually making a copy of the return value into S0. Okay, that's nice. And if we keep looking down here, we're not actually changing the value of S0 at all as we go through here until we load a copy back. And if you really wanted to, you could single step through and see that that was happening. So the main program isn't messing up the return value, so it must be something going wrong in the function. So thing to do is to go into the function, and you can see that this is where the function starts. If you bother to look up here, you'd see that the address for the max function is there. So we just go down to here, that one, set a breakpoint, and then we can run. All right, in fact, we could have set the breakpoint after we'd done all this stack setup stuff, because we're possibly not interested in that, but we could step through this, and if we wanted to keep a track of SP and FP just to make sure that they look like they were behaving themselves. We could do that. Okay, so then we get into the loop. And now, if we just single step like this, we've got to go through the loop 10 times. That's a bit tedious. So maybe we can set a breakpoint further down at the end of the loop. Jump back to max 4. Where's the end of the loop? In fact, as soon as we did that, we'd realise there was a problem, because we'd say, hey, wait a minute, I haven't actually set a value for V0. You can see that just by looking. But if you wanted to go right to the end of the function, potentially you could set a breakpoint here where it starts cleaning the stack up, and then you could keep running, and it would stop down here, and we can do a single step. But then we can start checking the values of the registers that we know that we used while the function was running. And if you go back to your code, you would see that we're using register S3 to hold the value of the largest value in the array. So the obvious thing to do at this point is to check the value in S3, which corresponds to register 19, I think, S3, yeah. And we see that's got the value 0. That's a little bit weird. In fact, that's extremely weird. Why would it have the value 0? And how do we get the value 4 coming back? Maybe if we're running inside here, I look up here and I see there's a value of 4 up there. There's another value for 4 here. V0 has the value 4. V0 is the return value register. It doesn't seem to have acquired the value of S3, which shouldn't ought to be 0. In fact, it ought to be the value of the largest. Maybe there's some other bug in the program. In any case, we'd see that V0 had that value. Why did V0, or how did V0 get that value? Well, in fact, I don't know where it got it. If we wanted to find out, we'd have to go back and step through. Let's just quickly do that. This is where it gets a bit tricky, going back to the start of the program. I don't want to clear any breakpoints. I want to go back and start executing here. And, that's right. And I think you can change the value of registers here. Whether this is actually going to work or not, I'm not 100% sure. 1, 2, 3, 4, 5. All right, so in theory, I've set the program to go back to the start, and I can try running it from there. So it actually stopped at the breakpoint down here, which is setting up the stack frame for max. So I could start looking for the register V0 getting set. And if you keep watching it up there, R2 doesn't seem to change, doesn't get changed, still doesn't get changed, still hasn't been changed, gone through the loop at least once or twice, still hasn't been changed, still hasn't been changed. Interesting, I wonder how it did end up with the value 4. All right, one thing to notice, you can see S2 keeps changing. That's our I variable. So we're up to 8. So we've almost finished our iterations through the array. Now S2 is 9. V0 is still 0. Isn't that interesting? And now we've reached the second breakpoint. All right, so we can keep single stepping. And we've gone back to the main program. This time, register V0 is equal to 0. So the first time it somehow got the value 4, second time it got the value 0. Looks to me a little bit like it might be getting random values that it's picking up from somewhere. Kind of makes sense because we're not setting its value at all. Right? But hopefully you would have noticed when you reach the end of the function that the value that should have been in S3, which was the largest value in the array, didn't get copied to V0. So you'd realise that there had been an error there. So that's what we get if we take out setting up the return value. So the way to check that, I reckon, would be to set a breakpoint straight after the call to the function and see what the value in the V0 register was when the function had just returned. What happens if we forget to return from a function? Let's try that. Attempt to execute a non-instruction at that address. Okay, what's the story there? So let's go back into QtSPIM. Let's reload the newly bugged program. And first thing we could do, since we've been given an address there, we could start looking, and clearly the address is a code address. Okay, 004, blah, 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 blah. That's an address in the code area. And we could start looking for that address. And if we go right to the bottom of the code, we see that the last address in the code is 400110. If we go back and have a look at the address that was mentioned here, 400114. Okay? So clearly we're looking at the next instruction, and according to QtSPIM, that doesn't correspond to anything in our code. Right? So we could run from the start. Let's do that anyway. Let's set a breakpoint. Where's a good place to set a break? Yeah, I'll set a breakpoint here again. And then just run from the start. Reaches a breakpoint pretty fast. In this case, we can see that the value of big is 8, because that was the largest value in the array. And we've actually set up the return value. That's nice. And if we start single-stepping through the code at this point, we try to do that next step, and it says attempt to execute non-instruction. Now, at this point, that might trigger the idea that, wait a minute, here we were cleaning up the stack, we were supposed to return to the calling function. And somehow that hasn't happened. It hasn't happened because there's no JR instruction there. You ought to be seeing a JR instruction at that point. All right, any questions on SPIM debugging? So that was a whole lot of different styles of bugs. So really it's a matter of observing what happens here for a start. Here, in this case, I got a wrong value. Right back at the start, I had an infinite loop. Here I attempt to execute a non-instruction. So the thing to do in this case would be try and find this address and see what was there. And you'll find that there's nothing there that looks like a piece of code. In this case, trying to work out why we got this weird 4 value rather than 8. So it obviously helps if you know what the result is supposed to be. You might think, hey, well, that looks kind of plausible. The program ran, it printed a number. The number was one of the numbers in the array. Didn't happen to be max, but if I hadn't bothered to check the array, I wouldn't know that. So you've got to know, exactly what result you expect. And up here, it was pretty clear that there was some kind of infinite loop because it didn't stop. And the very first bug that we put in just ran forever. So knowing the symptom can give you a few clues to get started. Incorrect value, infinite loop, weird instruction address. Why did I get there? So the next thing to do, get into QtSPIM and see if you can work out why things have happened. And the first thing I'd do with that is I'd look at that address and see what's there. Another way you can get a bit of a clue from things like this is if that address doesn't happen to be a multiple of 4, all instructions should lie on a 4-byte boundary. So if this didn't happen to be a multiple, it does happen to be a multiple of 4, so that's okay. But if it didn't, then some jump instruction in your program has jumped to an invalid address. So it's possible that the value in the return address register was wrong if you actually had a jump to the return address register. So you've got to think about possibilities like that. Right, so that'll do for MIPS. So next debugger to look at is quite different in the way, in the interface it provides. There are C debuggers. I'm not sure whether any of them are installed on the CSC machines at the moment. They're a little bit more graphical like QtSPIM is, but GDB, you're guaranteed to find that pretty much any machine you go to. So, it requires you to compile the program with -G. If you don't, you can't see any of the symbols, which makes debugging slightly tricky. Like QtSPIM, you can see the data structures in your program. There's a really cool command called print, which you can basically type any C expression at, and it will print the value of that expression, and it understands C data structures. So if the expression that you type is a struct, say, it'll print out the values of all the fields in the struct. And you can get it to print out an entire array and things like that. Well, I'll have a look at that anyway. You get access to the state via a number of commands, and these are the 3 that I thought of straight away because they're the ones I tend to use the most. The where command will give you a stack trace. So we all know what stacks are, we've seen them in MIPS, but the C function stack trace is often quite useful, especially if you get a crash like a segmentation fault or something like that. You want to find out whereabouts in the program it crashed. Of course, if you're using DCC, it'll tell you all that info, but if you don't have DCC, then that's probably the only way you're going to find out where your program stopped running. If it crashes in the middle of a library function, it's not helpful. Library functions don't have bugs, so you really want to find out whereabouts in your program the library function was called from that produced the error, and the up command will allow you to move up the stack frame. When you're trying to look at values of objects in GDB, it's all done relative to that current stack frame. So it knows the names of the object in the scope of that stack frame, and a stack frame corresponds to a function, essentially. So if you go up the stack to one of your functions, you'll be able to see the values of all the variables in your function. And if you want to find out what the code for the function is, then list will tell you that. So it's another way to deal with this. So GDB is a bit of a pain because you can't see the code at the same time as you're trying to do the debugging, but if you have a window with the code in it and a window with GDB, that's a reasonable sort of setup to try and do some debugging. You can set breakpoints like you did in MIPS. You can run the program, and when you run it, you basically type the command run, and then you type the normal command line arguments that you'd type when you actually ran the command. So that allows you to run with, different command line arguments. And step and next are annoying. They both they execute the next instruction. One of them, if the next instruction is a function, it will call a function and go on and completely finish the function and go into the next statement in the program. The other one will treat next as go into the function and execute the first statement inside the function. Okay, so subtle difference there. So let's have a look. Let's have a look. That'll do to get started. So here's a little main program I wrote. Someone pointed out on the forum yesterday that there was a bug in the trim function in the unlikely circumstance that the argument to trim was an empty string. So we can have a look at that in a minute. Most of the time in my SH, it's not an empty string, so you don't tend to notice the bug. All right, so this takes the first command line argument, says what it looks like. Now, the first command line argument could have spaces in it if you use quotes in the shell, and then it trims off the excess space at either end, and then tokenises it. So let's take a look. So that'll compile up the trim, and the code in trim is just that main program I showed you, plus the tokenise, plus the trim code from the assignment. So this is how it works. So if you've got one token, it'll tell you that. It'll trim. Trim doesn't make any difference in that case. But if you do have leading and trailing spaces, then trim gets rid of it. So you can see that's what argv1 is. It's actually got that space in it. Once you call trim, it gets rid of the space. And when you tokenise it, it shows you that you've got only one token. If you had something slightly more interesting, then you'd end up with something like that. So you've got the original input, you've got the trimmed input. You can see that spaces at either end have been gotten rid of, and then tokenise splits it into the three separate tokens. All right, what happens if you do this? Oh dear. All right, program crashes. Why does it crash? Good question. One thing to notice, when I compiled, I was using the -C option, so we've compiled in all of the stuff that GDB needs in order to take a look. So if I want to debug it, GDB with the name of the program. I don't think... Yeah, so I currently don't have a stack because I ran the program and it crashed, but I need to run it again to get the crash to happen inside GDB so it can check what the state was. So, well, if I run it like that, then we know it works. Starting the program, blah, blah, so... Oh, that's all right. Oops. Wrong machine. All right. So if I run it, then it runs correctly, and it even tells me process exited normally. Okay, so that's fine. It's harmless to run it in GDB. Now the problem was when I gave it an empty string. So it runs, prints out some stuff, and then tells me that there was a segmentation fault. In other words, a memory error. All right, well, it happens to have been in one of the library functions, in the strlen function. So we can double check that by typing where. So you kind of got to look for this part of the function. So strlen inside strdupe, inside trim.c inside tokenize, which calls strdupe, and we got main. So at the moment we're inside one of the library functions, and we don't know anything about the variables in the library function, so we can't really print anything. You know, we could say maybe there's a variable x here, no variable x in the current context. So we have to get to a context where we know what things are around, so we need to go up the stack. So this will take us up to this function, and if we go up again, we should end up in tokenize, and now we can actually see the line in the code where the error occurred. All right, let's start looking. So what's the value of I? I is 1, doesn't look totally implausible. What's the value of next? 0. Okay, so that's null value, so we're passing a null pointer to the strdupe function. Now you would have thought that the library functions would be a bit smarter in their handling of nulls, but apparently strdupe isn't, and if you pass in a null pointer, it'll go and try and use it and generate a segmentation fault. So in any case, we can see what the problem is. We've got a next value that's not a useful thing to pass to strdupe. So if we use the list, we can see whereabouts in the code we are, and the thing we want to find out is, all right, this is the line where things screwed up. We want to find out why they screwed up, or how we got to the point of next having a null value. Okay? So, if we look on the previous line, this is where next gets its value. So we call strtok, and it tries to get the first token. So remember, that's the way this whole thing works. Get the first token, stick it into the strings array, and then keep iterating until you bump into, or until you get a null from strtok, and then stop and set the value of the last entry in the strings array to be null, so you know you've reached the end of the tokens. So, what's wrong? In this case, if we wanted to, we could even have a look. What's the value of string? It's the empty string. Are there any tokens there? No. So, if we look at the while loop, we can see that strtok can return a value of null if there are no more tokens. And if there are no more, or if there are no tokens at all, the very first call to strtok is going to return null. And we haven't bothered to check for that. So if we did, we wouldn't have tried to make a new token when there isn't one to make. So it's all a matter of working out. I mean, GDB is good. The where will tell us, if we iterate up, it'll tell us what line of code it screwed up on. Often you don't end up with an error in a library function. It's more likely that it'll be somewhere in your code in the first place. And so you won't have to navigate your way up the stack. But if you do, you know what to do. So in any case, we worked out here was where the error was. I had a plausible kind of value. Next didn't have a plausible kind of value. No point passing a null pointer to strdupe. Where did the not useful value of next come from? Came from this line up here. Why did that happen? Well, because the string contained in temp. Oh, I could have checked that too. Actually, this is probably worth having a look. Okay, so temp is the empty string, but one thing to notice that you can see quite clearly from this is that this empty string is different to this empty string. It's a different string. They both happen to be empty strings, but they're located in different places in the memory. Right, so this one looks like it's on the stack. Any kind of high address like that is typically a stack address. And this one, you can see it's got one less digit in the address. It's located somewhere in the data area. In fact, it's located in the heap because strdup will malloc some space to hold the string that you give it. So in any case, both of those things are empty strings. We feed an empty string into strtoc. It's not going to find a token, so it's going to return a value of null. That null value gets assigned to next, and then we pass it through to strdup, and the program fails. So what to do about that? Yes, quit. All right, so let's go back to the C program. This is why it would be nice if I had one window here with the C code in and one window with the debugger, which I can't do on such a small screen, but you can easily do on the workstations in the lab. All right, so let's go back to tokenize, and it's down in here. So really what we ought to be doing is checking the only time we should do this is if we found at least one token. And then we can scan through all the other tokens. Always we have to terminate the list of tokens with a null. Okay, so we can't stick that inside the if statement. And of course we need to free up the memory that was allocated by the strdup. Oh, yeah, all right. I thought there was a memory leak, but I can see that we strdup up here, and then we free again down there. Actually, we're counting tokens up here. Oh, so we could have used the value of n that we computed. Duh. Although the value of n that we've computed isn't correct because we didn't bother to check whether that was null as well. So there are other bugs in the code. And in fact, I'm not sure why do we actually use n anywhere? No. So why are we even doing that? I don't know. That's a bit silly, isn't it? So I reckon that we could even just get rid of that chunk of code and it wouldn't affect the execution. That'll be interesting to see if it does. All right, so let's remake. Aha! Ah, that's why we need to count. All right. Let's see, go back there. Oh yeah, we did use n. We used it in the malloc. Thank you, C compiler, for pointing that out. Now, is that actually going to do the right thing? It's always going to allocate n+1 slots to hold char stars in the strings array. I guess it's kind of harmless if we don't bother checking there's at least one token, because n will end up being equal to 1 and we'll end up making 2 slots in the strings array, both of which will end up containing null. But, you know, if you wanted to be really strict about it, you wouldn't do this n++ unless you knew that the value that came back from here was not equal to null. So we could fix that as well. In fact, let's do it. Right, so that ought to fix it. So let's try a regular thing, so that still works. And let's try the tricky one, and if this crashes I'll be slightly annoyed. Good. All right, so there were no tokens to print out, so it doesn't print anything. All right, let's see what else I can break. No, that's... Let's remove this so we don't end up finding where the last non-space character is. Okay, looks all right. This is one scenario where maybe you don't actually even need GDB to work out what the problem is. And it turns out that it tokenizes correctly, but it's not trimming correctly. Okay, we can see that the trimmed version still has the spaces at the end. Now, maybe that doesn't matter, and it certainly doesn't seem to matter in this case. But if you wanted to, and you know, if it was important that that had really been trimmed, then you could use GDB and try and work out why. And to do that, you could probably set a breakpoint on the trim function. And then run with ABC. Okay, so we enter, oh yeah, I haven't actually showed you single stepping, so it's worth doing anyway. So, so at this point, in fact, right, uninitialized variable just contains some rubbish value. If we execute that statement up there, setting first equal to 0, then now first is equal to 0. Don't worry about this value, that's really what you're interested in. All right, if we do next, there really is only one white space. Okay, that's good. Now what's the value of first? 1. Okay, so I went round that loop once. So the next instruction we kind of didn't get to see that because it's all on the one line. Next, all right, we initialize those two variables. And it runs through that for loop. And then at this point, we'd be thinking, what's the value of last? It's 9. What's the length of the string? I'm guessing here that it might even work. Calling a function, it might not work. I don't know. The length of the string is 9. The value of last is 9. That shouldn't happen because there were some blanks at the end of the string. Let me see, what else did I want to show you with print? Let me guess. That does not do what I expected. I'm pretty sure that there's some syntax for printing out a sequence of values in an array. Anyone happen to know what it is? You can say print with an array name and get it to print out all of the values in that array. But I can't remember what the syntax is at this point. It'd be nice if this program had some struct in it, just so I can show you that it understands structs. Maybe I can add one. Add a gratuitous struct. That might be enough, actually. All right. I do need to do that after all. Let me see. There, I've used it. Hopefully that will keep the compiler quiet. Good. All right, GDB trim. Now, I guess I can set a breakpoint on main. That'd be pretty obvious, but another way you can set breakpoints, you can set them at... What did I do? Did I just type GDB without... I did. Right, so you can type list and it will tell you, it shows you part of the code, and you can run the command again and it will show you the next 10 lines, and then you could set a breakpoint by a line number, so you could say break 22, and then you can go run, and so it's stopped at that point, and if I want I can say print XX, and then it will print out the struct and tell me what the fields are and what the value for each field is. And if you've got pointers, it understands dereferencing pointers. Let's just execute Nick. And so if I say print string, then it will print null. Why is it doing that? Oh, because I did. Why is it doing that? Why is the argv1 equal to null? Correct, I didn't run it with any arguments, so let's start from the beginning, yes. Right, stop there, next. Right, so now there's a reference to, or it's referring to the string, and if I want, I can do things like dereference the character pointer, which will print out the first character in the string. I can also, and it will print out the blank, that blank there. And you can type in pretty much any C expression to print, so that makes print a very useful tool. But you've got to know, you need to know the context, whereabouts in the program am I? I'm in the main program. Given that I know that I'm in the main program, I can look at what all the local variables are and I can print out their values. So what other, and you can even print out things like that. And so on. Right, so setting breakpoints is extremely useful. If the program crashes, that's nice, because you can recompile it with -G, you can fire it up under GDB, you can run it again, you can make it crash at the same point, it'll tell you where it's crashed. And then you can start looking around at the values of variables at that point. if you notice a variable that clearly has a wrong value, then go back in the code to see where that variable got its value from and see if the mistake was there and blah, 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 trace back. If you can't work it out easily that way, then you could possibly set, if you know it crashes in a particular function, set a breakpoint on that function, run the program again, and step through that function. After each step, check the values of interesting variables, and if you do that enough, you should be able to work out where the offending variable has been set inappropriately. All right? Any questions on GDB? Best thing to do, go away and practice with it. Write a program, put a bug in it, and see if you can, It's a bit crappy if you put a bug in deliberately because you know where the bug is, and it turns out to be pretty easy to find it again. But maybe get a friend to put a bug in your program and then try and use one of the debuggers to work it out. All right, so practice before the prac exam next week would be a useful thing to do. If you don't, make sure you practice before the final exam using these debuggers, because you're bound to end up in a situation where your program doesn't work and you've got to try and fix it. And the easiest way to work it out is to use one of these tools. All right, that's it.